Today, we're going to talk about optical and visual illusions. Now, I've waxed poetically about how amazed I am at how quickly we put together a scene. It's not that we're seeing some objective view of the world per se. We Photoshop the scene, we color it with memory and salience, but we do, in less than a third of a second, grasp a scene quicker than we can really intellectually integrate. It's amazing, but we also get it wrong. We, how do we do that? Why? Well, some of it may be just attention or misperception. Or even, for example, a cognitive bias. Going back to the pre-Buddhist Vedic teachings, there's the story of a person who, in the dark of night, stumbles on what he takes to be a coiled, poisonous snake, and he runs away in panic. The next morning, he sees it was just a coiled rope. Well, okay, that was really supposed to be more a metaphor for our projections, for the kinds of things in our life, the phantoms, the chimera. But it also is just a cognitive bias. When a scene is not clear, you hear a sound in the bushes, you see a flitting in the bushes that could be a tiger or it could be a breeze or a bird. Well, you're going to probably, well, it's probably not a tiger for most of our experiences, but I'm talking evolutionary history. It's better to jump to the worst case scenario, depending on what that really implies, how many resources that takes, because, well, better to be safe than sorry. You don't want to mistake a rope for a coiled snake and vice versa, right? You don't want to, pick up the rope and find out that it's going to bite you and kill you. So there's that. But there's also simply distraction. There's also, for example, how do magicians work? They use gimmicks, they use contraptions, the old smoke and mirrors, and they also understand the psychology of distraction. By magicians here, I'm talking about stage musicians and illusionists. And we're taken in by it, but they have to understand perception, even with their gimmicks and gadgets and mirrors. Now, there could be ambiguity just inherent. If you're sitting in a train, you may have had this experience at a station, and the train next to you is also still stopped, and then suddenly you see the train next to you moving backwards, or are you moving forwards? Now, once you could feel the vibrations of your train or not, and then you realize what's happening, it just takes a second. But for that second, you may not be sure which one of you is moving just visually. I mean, really, think about the sun. How it's really obvious that the sun moves in the sky, but we know better. We have to intellectually project that we know that it's us moving, not the sun. Now, there are medical brain and psychiatric issues. One I've just actually recently read about is prosopometamorphopsia. Now, metamorphopsia is a distortion in vision. And as an ophthalmologist, we used to see that and be concerned about that, say, in macular degeneration or membranes in the retina. If you distort the retina, the image is going to be distorted. This, however, is a very specific distortion. It's a distortion in faces, and they call it demon face disorder. And you won't be surprised to hear, it's a temporal lobe. Remember, that's where the facial recognition area is, even though we know it's not specific only for faces. But this is very specific for faces, and faces just look distorted. It's incredibly rare, but it gives us some insight on how we process. These illusions give us insight into how our brains work. It's very rare, but maybe it's more common. One concern is, are people being diagnosed with psychiatric disorders when really this is what they have? It could be from trauma, tumors, strokes, and sometimes head injuries. We just don't always know. Now, there's also optical illusions. Now, an optical illusion, we all tend to, I think, no, maybe not all of us, but I've had a tendency to just lump all kind of these illusions that we're going to be seeing as optical. But optical illusions are a very specific thing. Optical illusions are due to the optics. Like the ray tracing we did where the arrow was upside down on your retina, the image is inverted. That's an optical question. Now let's look at this woman with her glasses. Now follow her forehead down, follow her cheek up, and you see the curve of her face behind the glasses is indented. Why? Because like 3 out of 4 people who need glasses, she's nearsighted, and the glasses lenses that correct nearsightedness, myopia, minimize the image. So it's like it shrinks the image behind the glasses. Farsighted enlarges them, so it would look magnified. So that's an optical illusion. It's purely due to the optics. Or these pencils in a glass of water. That's due to the fact that light moves more slowly in water, and then when it comes out of the water to the air, the light bends. It's refracted. The air-water interface difference, it works just like the lens in your glasses, and it bends the light. In this case, it makes the pencils look discontinuous in the water versus in the glass above the water. Is this just a fun fact? No, I mean, here's an example that, by the way, shows up on college physics exams when you're studying optics, or ophthalmology or optometry boards will have some similar problems. And we see on the upper left a bird, a diving bird that wants to go after the fish. On the lower right, we see 2 fish. The lower fish is where the fish really is. And you see the light that's going to end up from a certain point in that fish, end up in that bird's eye. First goes through the water below the line. Water is denser, goes into the air, so light bends. And there's a simple formula for that. We don't have to go. It's called Snell's law. It's just trigonometry. And it's very deep what's behind all this, I mean, the physics, but that doesn't concern us. It bends the light. Now, what the bird sees is that bent blue line that's in the air. And if you follow it back, follow the dotted red line, that's where that bird sees the fish. It sees it more shallow and further away. That diving bird is going to have to adjust to that, besides all the other things like the fish is moving and the water might be cloudy and ripples and so on. But that's an optical illusion that is real and evolution has to deal with. Well, at least the bird does. Now, visual illusions are more complex. This is eye-brain interaction. These are sometimes just kind of tricks, and we'll go over that. But they reflect how the eye and brain works, the shortcuts it takes, maybe to save time and energy, so we build those scenes right away. It's what we expect, perhaps. It's hard to know how much of that is built in versus how much of that is cultural, but they're very deep. They're very deep. They're sometimes really hard to shake, even when you know the answer. They seem to help us predict the future. That's the idea of, like, we see what we see, what's going to be the next step, what's really there. Well, let's take motion for an example, because you know about this from, traditional films and animation, where you had still images that our brain ties together as motion. So we know that's actually a kind of illusion. It's not an optical illusion per se. It's called flicker fusion. It's how fast our retinas and brains can tie it together. And this is really an illusion when we watch an old movie that's on film stock or a flip book or animation. This became of great interest to scientists and artists around the turn of the 19th to 20th centuries, when the shutter speeds on cameras were fast enough and could be timed to strobe lights so that they could do things like study how a horse really runs. It wasn't always clear. Are all feet off the ground at the same time? And artists got interested in that. And here we see a Cubist painting by Duchamp, New Descending Staircase 2 in 1912, showing this kind of strobe-like effect in motion. Now, motion is not something we're going to talk about in detail here, but think about this for a second. you can argue, oh, if a butterfly comes by, it flicks across my retina, and somehow my brain just figures that out. But what if you're following that butterfly? I mean, with your eyes or your head. Well, it's not flicking across your retina. You're trying to keep it on your fovea. Now, you may be able to sense that your eye is moving. There may be multiple feedback mechanisms, of course. But one of the things that happens is the foreground versus the background. The butterfly is moving against a still background as your eye moves. So how do we not sense movement every time we move our head? Like with the train that I mentioned, sometimes we will get fooled by that, but generally we don't. We don't walk down the street thinking the street is moving every time we turn our head, or through our house or whatever. So it's really pretty complex in that sense. And here's a good simple little experiment you can do that shows you. It's called parallax. Very important, but simple to demonstrate. Hold your thumb out and look at something that's 15, 20 feet away, close one eye, then the other. You'll see your thumb move back and forth, and may cover much of the object, but the object doesn't move or moves minimally. And that's a way to judge foreground and background. We learn that. Hard to know how much of that's hardwired. But figure background is important when we think of optical illusions. The Gestalt psychologists in the early 20th century were very interested in this. And so this is an illusion that you're probably familiar with. You've probably seen a million times, face and vase. And really all it is, as this cutout shows, is are you paying attention to the background or the foreground? Just look at the illusion and do that. Just say, I'm going to look at the background, I'm going to look at the foreground, and I'm going to switch them. And you'll see it works. Now, here's something related, also of interest in terms of Gestalt studies of perception. There's, how many triangles do you see? Now, if you're clever, you might say, well, there's clearly no triangles. There are these, three, bent lines, and there's three Pac-Man-like things, and there's no real triangle there. Yeah, but you see two triangles, don't you? And if not, I'm kind of surprised, because it's hard for me not to see two triangles. And why? Well, first of all, there's the principle of knowing that something in the background could be covered by something in the foreground. And we're just going to make that assumption. Remember, we like lines, we like geometric shapes. And so we extrapolate those. There's the rule of good continuity. The lines for the linear triangle, not the upside down white triangle, we just read them as discontinuous, and we fill them in and just assume that there's something in front of them, because that's how our world tends to react. So the white triangle in the front, and some people will actually see it as a little whiter than the background. I don't tend to. That triangle really doesn't exist any more than the other triangle does. Yes, there is in reality no triangle there, but it's true that you will most likely see two triangles. Now, again, a lot of this are tricks of trying to see light or continuity, foreground, background, or in this case, again, light, images, how it affects a two-dimensional image, that we're mimicking what we see in three-dimensional worlds. That's a lot of these illusions. Remember, we don't see true 3D. Stereo vision is not necessarily true 3D, because it's two-dimensional images that are just overlapping a little bit. Again, it's a brain trick when we see stereo images up close. If you don't have two good working eyes, if you have amblyopia or a problem with one eye, you may not develop stereo vision. You may not have stereo vision, but you can still judge distance. And this plays with that, plays with those cues. In this case, we have a square on the left that looks like everything is indented. If you turn it upside down, you get the square on the right where it looks like the image is coming out at you. That's just due to the shadows. We assume, by experience and perhaps long millions of years of evolutionary experience, as well as our personal experience, that light generally comes from the top. And if it's ambiguous to where it's coming from, that's the assumption our brains and eyes are going to make. So on the left image, the light coming from the top hits the bottom rim, so it has to be indented. On the right, it hits the top rim, and so we read that as coming out at us, which that means the top would catch the light and shadow on the bottom. Again, our assumptions and experience. Now, as far as experience, we also know to compare to what's going on. Remember, we talked about that with the dress. Now here, this is an illusion many of you are well aware of. We expect a dark, we'll look at the two x's, the two squares with x's, and we see the darker x on the lower right as darker than the x right near the ball in the shadow. Well, we know, because you've probably seen the illusion, that they're not, but can you really see those as the same color? You see that there's a little part in the diagram that says cut them out. I mean, after all, we're comparing to the other squares adjacent to it. And that alters things. So it says cut them out, so I did. And here I cut them out, and you can see, indeed, they're not just fooling us. It really is the same color. But can you really see that even when you know the answer? As I said, a lot of this is us projecting a 3D world because that's our experience, both in terms of evolution and personal. So here we see a cube. No, we don't. What we really see is a bunch of straight lines. And we construct it as a cube. Now, I want to ask you, where's the front face of that cube? It's either going to be down and to the left or up and to the right, as we see below. And you can make yourself see either one if you just pay attention, say, all right, I'm going to see it as going up and right, or I'm going to see it as going down and left. And you'll see nothing in between. It's one or the other. I personally always gravitate to the down and right, but I can instantly change it to up and left. Similarly, we know that parallel lines don't stay parallel when they're going off to the distance, right? They converge. We see like railroad tracks and roads. We have perspective lines. And certainly this has been codified back 500 years ago in the early Renaissance. But there's clearly some evidence that maybe less formally, but people knew about this way before that. And yet, what if there were no roads? What if you evolved in a forest? What if you were just in an open savanna? This may not be as strong in your experience. So in this illusion, those two blue lines are the same as you see on the right, but we tend to read the upper one as bigger because it covers 3 perspective lines instead of 1. And we know our brain is just socked in for perspective lines. It's just part of what we know. And perspective, you could play with it. So here you see these two tables. I can never, right now I'm staring at them, I cannot see them as the same. So I did what they said again. I cut them out. Here you see the cutout one on top of the other table. And then here you see I took that cutout and put it on top of the table, and they're clearly the same. I cannot see that as true. So I wondered why that is. And part of it is that, look at those legs. There's no way those legs are going down perpendicularly from those tables. We read it that way. We read that as 3-dimensional. But the shadow implies we're looking almost straight down. And yet those legs are coming kind of out at us. Even knowing that, it doesn't help. But I wanted to just play around with it. And there is also another effect, before I show you what I did, is that we tend to see vertical lines as longer than horizontal. I don't find that a strong effect for me, but I do see it. And what does that mean? Why should that be? Well, most things of interest to us are usually vertical. That's one idea anyway. Just so story is true, but that seems to be. Now, I've seen people talk about studies where maybe just being a little off from vertical is a little more natural and actually preferred. So, in the table's case, we have kind of 2 effects here. When we get rid of the legs and the shadow, you see they look closer together. And one idea is something called the Mueller-Lyer effect. That is that the legs are acting. Here you see the Mueller-Lyer effect. And when you have those carrots, those angled lines going outward, the line looks longer than when they're going inward. But you see the lines are the same. And some of that, I think, maybe is what the legs were doing. So I masked the legs, and indeed, it's much closer. There may be multiple things going on. I also now turned it 90 degrees. So the other one is vertical, and to see if there's some of that vertical effect. And maybe I can convince myself there's a little bit of that. But again, even knowing it, let me show you again. Can you really see those two tabletops as the same? Now, the Mueller-Lyer effect is kind of interesting because this is one of those effects that people have done, that people did a study where they think it's really cultural, because they said, well, maybe it's due to built environments. We see those carrots, those angled lines, as a perspective that, like, built carpentry, Western architecture, we're used to that, right? Square buildings and furniture and so on. And then they did a study in South Africa where South Africans of European descent were taken in more often by this illusion than Kalahari hunter-gatherers. But then there could have been other cultural things involved. It's hard to know. And other studies, including where computers were trained to try and judge these things, and I'm not expert on what they did with those computers, the computer was fooled by this. And also there's this illusion, a form of the Mueller-Lyer, where it isn't. We have round ends, and the illusion holds. Now, it just feels hardwired, right? I mean, they're so persistent, even when you know the answer. But assuming normal vision, is that the case? Well, yes and no. You know, maybe it's learned, but really relatively hardwired, just like once it's learned, just like the language a baby learns, or learning to walk, right? I mean, you don't have to think about walking. You had to learn it, but then it's kind of really in there. Under non-pathologic situations, you're going to remember how to walk, even if you're pretty disabled, mentally, drunk, whatever. You may not physically be able to do it, but you know how to walk. Same thing where you put on the prism glasses and you learn to ride a motorcycle with an inverted image. Even though we spent our entire life without those prism glasses. So there can be a kind of learning that's not like, when we learn dates in history that we're just going to forget, or, how to do a certain algebra problem. Can some of this be cultural? Absolutely. Or environmental, like I mentioned about if you were brought up in a forest, or, versus in an area where there are roads and buildings and so on. And remember, even rainbows are kind of optical illusions, and the blind spot is filled in. We live with illusions that we just take for granted. So the neuroscientist Dale Purves, in one article, wrote the following. So let me read this to you. Everything we perceive, and it was an article about visual illusions, one illusion in particular that not everybody sees. So he said, still, his comment was, everything we perceive is inconsistent with the physical reality of the world. Everything we see, whether it's length, color, brightness, you name it. So you're not really being tricked. Instead, visual illusions help reveal what our mind's eye is up to. I like that. That's what we've been talking about all along. I mean, can it be any more about projections and chimera that we fashion to protect us from the onslaught, in this case, of information, from dangers, to tell us what has worked in our lives and how to navigate our lives, to try and get us through the pain and uncertainty of life to a thriving world that we can deal with? Kind of, yeah. I mean, in a sense, it's all optical and visual illusions when we're talking about vision. It's tempered by our expectations, our conditioning, both evolutionary and personal. By conditioning, I mean experiencing the experiences that teach us. And it's the vast fluid web of life and the universe unfolding. Yeah, it really is that grandiose, because that all comes into play to get us where we are. We need the world as it is for us to have evolved as we have, because we've evolved to deal with the world as it is, and the world as it is goes back to how the universe has evolved. Now, our other senses, by the way, are much the same. I've centered on vision, first of all, because it's very important to us as humans and it takes up a lot of our brain. But it really is, in various degrees, true of other senses as well. So, besides the gee whiz and the interest, what does this really mean? I mean, I started off talking about how we build a life and a deathbed experience by Laplace. Well, let's return to that in our next talk and wrap this up. Thank you very much. See ya.